Now it is my pleasure to introduce you to one of the most commonly used confidence intervals in statistics, t-based confidence intervals. In the previous video, you learned about a t-statistic and a t-distribution. Let's see how these two concepts tie together. If the sampling distribution of the mean is normal, then the distribution of the t-statistic is a t-distribution with n-1 degrees of freedom. A normal distribution of scores, or a large enough sample to invoke the central limit theorem, will assure us of a normal sampling distribution of the mean. That means that we can frequently rely on the t-statistic being distributed like a t-distribution. Which t-distribution? The one with n-1 degrees of freedom, where n is the sample size. Confidence intervals based on the t-statistic are among the most common confidence intervals in the research literature. So now let's talk about inference for the mean of a population. All possible values of the population mean can be hypothesized to form a confidence interval for the population mean. Yet if you have been watching my video series, you know that a shortcut is to add and subtract the margin of error to the sample mean. A t-based confidence interval looks just like a z-based confidence interval. That is, you have a sample mean and you subtract and add the margin of error in order to get your confidence interval. Subtracting will give you the lower bound, adding will give you the upper bound. There are two differences here from z-based confidence intervals. First, we're using the t-statistic instead of a z-statistic, and so therefore we're going to calculate our critical value based upon the t-distribution. Second, the reason we're using a t-statistic is that because we are using the sample standard deviation divided by the square root of the sample size, in other words, the standard error of the mean. Multiplying the t critical value times the standard error of the mean gives you a margin of error that we can then use to form a confidence interval. Let me show you how this works using R. Here's an example. In 2010, an Ohio newspaper collected water samples from Ohio state parks. They sent the samples to a laboratory to test for coliform bacteria. Ohio has a safety standard of less than 400 coliform bacteria per 100 milliliters of water. Here are the coliform bacteria counts from randomly collected water samples in Ohio state parks. I'm going to enter these into R. I don't know how many there are without actually counting. Fortunately, R has a function for counting. It's called length. So I'm going to see the length of this vector, which in essence means how many water samples do we have. It looks like we have 20. Here's a box plot. If 400 is the safety standard, it looks like Ohio state parks are not very safe when it comes to their water. As you can see, in most of the distribution, there is a coliform bacteria count of greater than 400 per 100 milliliter of water. We can also get the sample statistics, the 5-number summary, and the mean. And I see here that the mean is 1,231 coliform bacteria per 100 milliliter of water. And the standard deviation, which is 1,037, meaning there's quite a wide range of the amount of bacteria in water depending upon which state park you go to. I'm going to save that mean and standard deviation. And now I'm going to use the standard deviation to calculate the standard error of the mean by dividing by the square root of 20. I'm now going to calculate the t critical value. I want a 95% confidence interval, so I'm going to get the percentile that is at the 97.5 percentile rank. That is, I want 97.5% of the area beneath my percentile. I need to specify which t-distribution. It's going to be the one with 19 degrees of freedom, that is n-1. I can now take that standard error and that t-critical value and multiply them to get a margin of error. The margin of error is 486 coliform bacteria per 100 milliliters. Let's get the lower bound by taking the mean of our sample and subtracting the margin of error, and also the upper bound. What we have found is that the average number of coliform bacteria in 100 milliliters of water in Ohio state parks when the newspaper collected these samples is somewhere between 745 and 1717. Actually about 746 and 1717. Interestingly, the safety standard of 400 is not even in this confidence interval, so the mean is going to be an unsafe value. Let's try one more example. This comes from a chimpanzee collaboration study. Chimpanzees were given a task in which they had to collaborate if they were going to get the food that was available to them. Each chimp was provided 24 trials to see how many times he or she would collaborate. The sample size is 8. Let's get a box plot for this small sample. Fortunately, even though it's a small sample, it looks to be fairly symmetrical. It appears as the median is somewhere around 19. So out of 24 trials, about 50% of the chimps tried more than 19 times to collaborate to get food, and about 50% of the chimps tried fewer than 19 times to collaborate to get food. Here's the 5-number summary and the standard deviation to go with it. I see the mean is 19.6. And now I'm going to introduce you to a function that will probably be one of your favorites. It's called t-test, t.test. When I run t-test on the sample data, I obtain some output that includes a 95% confidence interval. The confidence interval ranges from 16.5 to 22.8. So what I've just determined is that for this sample of 8 chimps, their average number of collaborations out of 24 trials was about 20. That's pretty collaborative. But if we extended this to the larger population of chimps, those that were not included in this study, we would expect the average for all chimps to be a collaboration frequency somewhere between about 16 and 23. Once again, I think that even for the population, this shows that chimps are highly collaborative. Out of 24 trials, 16 is at the bottom of my confidence interval, and it could go as high as 23 for the average number of collaborations. So that's it. That's how you construct a t-based confidence interval for the population mean using the sample mean with R.